Right, good evening again, class, and welcome to our 8th class, presentation 4, 6, 7, 7th class, I believe. Let me check. 1, 2, 3, 4, 5, 6, 7. Yeah, so this would have been the 7th class. Right, so 7th class on March 24th. So this is where we are. Wait, before that, I hope you all are doing well. Things seem to be getting worse. So we're up to like 51 cases now, I believe. So I hope you all, doing the socially responsible thing and isolating and washing your hands properly and all of those things. I mean, we all doing the proper thing right now. We all staying home and watching our Cisco videos from home instead of, congregating in our class. So yeah, you all have a ton of things to do while you're home. So watch these videos, watch these CBT Nuggets videos if you need to. Read the textbook if you could. And we'll practice whatever practice questions you could in the miscellaneous folder there. But for now, I think you should leave the questions out and focus on learning the materials. Don't just learn to pass the exam. Actually try to memorize the materials and understand the material, and we'll focus on the questions afterwards. Right, so we, believe it or not, we covered all of these things. It may seem bad that we still stuck in section 1 and we have all of these things to go, but don't worry, we are on track. Section 1 is it's crazy. You have all of these topics, and the other sections are a lot shorter. I'm not sure why they cram so many things in the section 1. They probably wanted to make sure you all have the foundations set, and then we'll go into the more complex topics. Right, so we covered all of these things, and at the start of the presentation I have a brief review of the interface and cable issues, and then TCP and UDP, and a bit about the IPv4 addressing and subnetting as well. So we'll do a brief recap on that at the start of this class, and then we'll dive in to some more topics. So last class we only got to go through 1.6, configure and verify IPv4 addressing and subnetting, because subnetting is such a large topic, and it is. I know you're not overwhelmed by yourself. Everyone, once they reach in the CCNA, they all say that subnetting is if not then at least one of the most difficult topics that is here. So take your time with it, don't feel intimidated, just keep practicing. Take your time and learn one question by one question, and after a while it'll become second nature. You'll see the patterns and the flows, and you'll be able to do it very quickly, don't worry. But for this class, I can't take too many more videos and topics going over these practice questions, because we have all of these other topics. I mean, it doesn't make sense that you understand subnetting like the back of your hand and then you don't understand the rest of the stuff. So I want to go on today, and afterwards we could practice more subnetting questions after we've covered all the material in the course. Yeah. Right, so today we'll be going through 1.7, 8, and 9. So 3 slightly medium-ish topics, not very heavy. In fact, I think 1.7 is fairly straightforward. 1.8 will be mostly labs. Any topic that starts with configure, I won't do too much of it in the actual presentations, because configurations obviously are made to be configured. So in the labs you will actually cover these topics, and I made sure that you at least have one lab for each configuration topic, so you could actually know to do this topic. So when you read configure and verify IPv6 addressing and prefixes, you know how to configure and verify IPv6 addresses and prefixes. It's not just that you read it and you kind of know the commands, it's that you actually went in a switch or a router and you have done it before. So I can't remember which lab exactly this is, but you will do this in a lab. But for this class, we will just go over some of the basic topics, just so you get your hands wet with it, feet wet, yeah. So we'll go through these, and yeah, let's start the presentation now. Let's see, that should come up there. Good, right. Right, so welcome to the starter presentation 4 again. In this class, we're gonna, we still in network fundamentals. We're gonna go through the need for private IPv4 addressing, configuring IPv6 addresses and prefixes, and comparing IPv6 address types. And in the second half of this week, so the next class, we'll go over verifying IP parameters on Macs, Windows, and Linux machines, and then some wireless principles. Cisco added a lot of wireless stuff into this version of the CCNA. Okay. So last class we discussed several issues on interfaces and cables that we may come across frequently in our field. Can you remember any of these issues? So list some of, well, not all, but list however many of the common interface and cabling errors that you can remember from last class, along with a brief description of each of them. So whichever ones you can remember, whichever ones, off the top of your head, write them down and put a short description of how you would describe each of them. Yeah, so pause the video now and try to do it. These things will pop up very, very frequently. So if you could remember anything in this section, you will impress a lot of engineers on the field, because they will encounter this daily. Okay, so pause now and continue. Okay, so here are some examples. Network collisions are one common interface and cabling issue. So network collisions occur on link with shared collision domains when two hosts attempt to transmit simultaneously. So last class, and I believe the class before as well, we went over a lot of discussion on what collisions are and how we largely mitigated those problems in modern day networks with switches as opposed to hubs. But you'll see here it still happens. We have the counters incrementing here. I don't know if I mentioned counters in last class, but basically all of these numbers here are counters. So it's a counter to keep count of something, basically. So when you hear someone say check the counter, this is what you're going to do. You're going to run a command like this, maybe not this exact show interface and the interface name, but something similar to this, and you're going to be looking at a number like this. So for instance, the CRC counter here is 0, whereas the collision counter here is 10. Yeah. So network collisions are just one issue that we may come across. Input or CRC errors are another issue. So these errors occur when bits get corrupted during the transmission of a frame across a network. So you see here we have a ton of input errors, a ton of CRC errors, a ton of frame errors, and no overrun errors, no ignored errors. Yeah. So these are the counters that we look out for to tell us that there is, there are these types of errors on a network. We may also have duplex or speed mismatches. So you'll see here, if we do a show interface and then the interface name, we see the speed, right? So the bandwidth there, and the duplex, right? Full duplex. Sorry, not the bandwidth and speed. I believe this should be the same number. Yeah. So 100 megs, but you can see it easily just on this single line here. So full duplex, 100 megs per second, and it even tells you the media type. So you see this, the interface could only support 10/100, which means it could operate at either 10 megabits per second or 100 megabits per second. And we are at 100 megabits per second. So this link is operating optimally. If we saw that this was a 10/100/1000 link, and this was 100 megs, then we know something is wrong here. This link is not operating optimally because it could support 1000 megs and it only runs as 100 megs, for example. But right now it's still 10/100 and it's running at 100 megs, so we're fine. And well, of course, we mainly want to look out for duplex and speed mismatches. So if one of your sides saying half duplex and the other one saying full duplex, then clearly you have a problem across the link. Because both sides needs to be half duplex or both sides need to be full duplex. And in modern networks, there really is no need for half duplex. Most of your stuff should be running at full duplex and either 100 megs or a full gig or 10 gigs or more. And both sides should be matched with those parameters. And of course, we have many more issues, so check back your notes from last week to recap some more of those issues in case anything as just said sounded Spanish to you. So let's recap our two favorite transport layer protocols now, TCP and UDP. Can you remember the main differences between them? Again, take a pause and see if you could just list out a few quick differences between them. Okay, so just to recap, TCP provides reliable in-order connection, a reliable in-order connection-oriented service, while UDP provides an unreliable, best-effort connection-less service. So you see the direct comparisons there: reliable versus unreliable, in-order connection-oriented versus best-effort connection-less. Technically, TCP is best-effort as well, but definitely the reliable versus unreliable part, in order versus not in order at all, and connection oriented versus connectionless. So they are both used by a variety of applications depending on what the requirements of the applications are. They each have their own sets of advantages and disadvantages, as we explored a lot last class and as we will recap now. So remember, this whole process is only for TCP. So we had this thing called the special three-way handshake, which is usually between a client and a server, but you could use it between two servers and two clients. It doesn't really matter. As long as they're using TCP, they need to go through this process. So we explain the whole, whenever anybody asks you what the three-way handshake is, if you tell them it's a SYN and then a SYN-ACK and then an ACK, then they know you know what you're talking about. If you could just remember that, then you're on the right ball. Well, you're in the ballpark, basically. So the whole point of the SYN, ACK, and ACK was to synchronize sequence numbers, right? So we went through the sequence numbers, where we said we start off with a random number, for instance 100 from the client, and the server will ACK with the sequence number just one above that, or just something a bit higher, to tell the client here, in this case, that they acknowledge the sequence number 100 and they're expecting 101 to come next. And at the same time, they are sending their own sequence number, which doesn't need to line up with this client sequence number at all. They're sending their own. And then, of course, the server needs to know that the client got that sequence number. So the client will send an ACK for the number just above that sequence number. And he will, of course, send this using his own sequence number, which is 101, because he used 100 in his last message. Yeah, and you see after that, his state changes to established. So during this process, we'll have different states as well. So SYN sent, because he sent a sent. SYN received, because he received one. Then he is established at this point, and when he gets the ACK here, he is established. So both sides are established now. Therefore, the connection is formed, which is where we get the connection-oriented service from. And therefore, they can start transferring data. So all of this happens before any data can be transferred. So now that you understand a bit about TCP, let's explore UDP a bit. So UDP provides a completely connectionless service. If a transmitting device wants to send data to a receiving device, it does not need to go through any connection setup process, as we saw previously with TCP. It just starts sending. So this whole madness here, we don't need to go through that with UDP at all. We just start sending the data that we want to send. So you see here, host 1 wants to send the alphabet to host 2, so it just starts sending A, B, C, just starts sending. Don't waste any time setting up all of that madness. So you can see advantages of both, and we went through that last class. If B is lost here with UDP, host 2 has no way to communicate with host 1 and tell them, hey, resend B, I didn't get it, because this is completely one way here, and he has no way to know that host 1 tried to send B, because he has no sequence number tagged to this to keep track of all this data. Yeah. And then of course we went through IPv4 address configuration and subnetting, which was the big topic for last class. So I hope you've been practicing your subnetting. Remember, Cisco has historically loved to test this concept in the CCNA. So we don't know a lot of the questions that Cisco will bring in this class, in this exam, because they're still releasing questions, and it's a very new exam. It just came out basically this month. So this is all very new. But in the last version, definitely Cisco tested a lot of subnetting, which is why we spent as much time as we did. So that's why I said keep practicing, but we can't spend the whole class, the whole course doing that one topic. So just to recap, we saw first how we can use a special table to convert an IPv4 address from decimal notation, which is what we know here, 192.168.1.1, to binary notation, which is this whole thing, dot this whole thing, dot this whole thing, dot this whole thing. and of course these dots are just there to kind of draw the parallel here, but in a real binary number you don't have these dots either. It's just a big long string of 1 and 0s. So this is of course what we did to convert from decimal into binary. Remember we did this whole thing where we took the first number, and then we wrote out our headers here, and we wrote out the actual number there. We took this number and we said how many times can 192 go into 128, and then the remainder, and then how much it could go into that, and then how much it could go into this, and then this, and then we wrote the 1 if it could fit, or we wrote the 0 if it couldn't fit. And this was our binary number, sorry. So yeah, this was like the meat of the last class, and this is what you need to know. And then therefore the decimal number 192 is equivalent to the binary number 11000000. We then repeat the same above process for other decimal numbers 168, 1, and 2, and we get all of their binary equivalents, and then we write our complete number in binary. So by now I hope at least this part makes sense to you. And of course, if you don't understand the table at all and you don't understand how to use the table, feel free to go and look for some other methods. There are the long division methods. There are other methods out there, but you aren't allowed you could use on a scientific calculator as well, but you aren't allowed the calculator in the exam, which is why you need to know a method. And whichever method you choose, just pick it and learn to do it fairly quickly, because as you've seen, this isn't the actual question, right? Cisco won't ask you a question like convert 192 into binary, sorry. This is just part of a bigger question, which you'll need to understand this, and you'll need to understand this to solve the bigger question. So just pick a method and practice it as much as you can until you're comfortable with it, and then we'll move on from there. Right, and of course we saw how we can reverse this concept to convert numbers from the binary notation back into the decimal notation. So that was what this slide was explaining. So to convert from binary to decimal, we simply reverse the process. Take the following binary number as an example. So 4 1s and 4 0s. We draw up the same exact table, and we just put our 4 1s and 4 0s, and then we just start multiplying. So then we simply multiply our numbers in each column and sum them at the bottom row. So 128 by 1, plus 64 by 1, plus 32 by 1, plus 16 by 1, plus all of these numbers here by 0, which will basically give us 0. And we just sum all of these things to get 240 in decimal. So we use these concepts to explain the concept of IP addresses and their networks or subnet masks. So we based on our new understanding of the binary equivalent to these decimal numbers, we now understand the significance of subnet masks and how to get all of those important bits of information if we given an IP address and a subnet mask, right? Remember the whole binary ANDing and getting the network address, and then the broadcast address, and then the first usable IP, and all of those things. So all of that was based on our understanding of binary addresses here. And of course we started off with these old classless networks, classful. Let me edit this one time. Classful. Yeah. So these classful addresses, these classful networks, were the giant networks that IPv4 addresses were once grouped in. So they are still kind of relevant, but largely they're not. And in this class, we'll actually go into why things change so much, and why people don't use classful networks anymore. So CIDR, or classless interdomain routing, is the new method of working with IPv4 addresses. Many years ago, IPv4 addresses were regarded as classful addresses and could only be handed out in giant blocks, as illustrated in the table below. Now with the advent of subnetting, we have broken these old large blocks up, and now addresses are written in CIDR notation, like 172.30.10.6/24. So yeah, we went through this last class as well. Once upon a time, you could have gone to a regional internet registry and asked them for a whole /8 of addresses, or a whole /16, or a whole /24, and they would have given you a giant block like that, based on how big your organization is. Now we don't have that luxury anymore because we have run out of IPv4 addresses. So because of this now, what people are doing is they're taking these large /8 blocks and they're breaking them up using this magical thing that we just found called subnetting. So for instance, a big organization might be assigned a /24 and they might need to use subnetting now to maximize the use of that /24. So they can't just have one network using that whole /24. They need to make sure that all the networks in their organization can use the addresses in that /24. So they would break up the /24 and create /25s or /26s or /27s and maximize that IP address space usage. So we showed how we can take large network blocks and break them up into smaller blocks for more efficient use of IP space. We did this by finding our network address, converting it into the binary space, and then borrowing bits from our host portion to create as many subnets as we need of appropriate sizes. So that is of course what we discussed in the last class. That was the theory behind subnetting. We take our initial block and we borrow some host bits and we turn those into the new subnet bits as well, and from the remaining host bits we assign hosts. So we basically make smaller networks, which is all that we did in the last, in the small video and the last big video as well. So I really wish I could spend multiple classes doing practice exercises with subnetting, but as you can see, the syllabus asks us to cover way too many other topics. So make sure you practice at the site I linked before, which was subnettingpractice.com or something, and feel free to go ahead and practice in whatever other sites you find. Just Google subnetting practice and you're sure to find other links. They are, as I said, it gets very deep, so don't spend too much time just doing subnetting. Make sure you're comfortable with the other material as well. Now this is how I look at subnetting, and I wanted to show you all this as well. So this is another way to look at subnetting. You may come across a term called VLSM, or variable length subnet masks. That simply means you could create subnets of different sizes. So if you look at the bigger picture in the, for example, in the last question that we did on Saturday, in the small video I made, you realize that we created two subnets of identical sizes, right? So if you create, if you subnet from a /24 and you break it up into two subnets, you'll get two /25 subnets. If you break up a /25, you'll get two /26 subnets. But the idea here is that you do not need to address your host from these two blocks alone. So for instance, a business might say, okay, I have a /24 that I've been assigned. I want to break that up once and break it up into two /25s, but then I have maybe one big network for my data center that needs this whole /25, but the other /25 I want to break up even more because I have some smaller networks. So they would take that /25 and they would break it up into two /26s while leaving that /25 by itself. And then maybe they'll leave one /26 and take the other one and break it up into two /27s. So remember, so this is like the next step in subnetting, I would say. So from the last two classes, the last two videos, you should have an idea of how to go from here to here. So this is your equivalent of borrowing one bit. So if you borrow one bit into your subnet mask, and you create two subnets, you'll realize that you get two /25s. So all that is done after this is that they took one of those subnets and they borrowed another bit. So they left the first subnet by itself. So think of subnet 1, no subnet 0. They just left that by itself, and with the second subnet here, they borrowed another bit and they created two subnets from this subnet. So they subnetted it further, and then from this now they had two new subnets, and in this case they left the second subnet by itself and they took the first subnet and borrowed another bit to create two /27s. So this is what VLSM is all about. Remember when I said don't worry about it too much, focus on the core concepts first. So this is where it leads you basically, and this is where we are in the networking field now. We go all the way down to /31s sometimes, or /30s depending on what the equipment supports. So we'll take a /31 or a /30 for like a point-to-point link. So between two routers we'll use a /31 or a /30, and then for the bigger networks, obviously if we have something big that needs a /25, we'll dedicate a whole /25 for it. Else, if we don't need such big networks, we'll break it up and we'll try to maximize the use of our IP space like this. And you'll see why in this class. So now on to the new material for this week. Yeah, so that whole thing was a recap, and now we're going to start some new material. 1 second. Right, just got some coffee there. So we're back onto our new material. So this is what I've been mentioning, I guess, since the start of the class and the start of the course. This is the sad state of affairs in the world of networking. And as future network engineers, you all need to appreciate this, which is why Cisco put it in their syllabus, because it impacts everything basically. So it is the need for private IPv4 addressing. So IPv4 addresses can be categorized in a number of ways, but one of the most popular categorizations is in the whole group of public addresses versus private addresses. So the private address space, also called the RFC 1918 space, which is just the number of the IETF RFC. So for those of you who have never seen an RFC, let me pull up one now. Actually, I'm going to pull up this RFC now. Let's see. Yes. Go back. Close. Right. RFC 1918. Right. So the RFCs are freely accessible. Just Google whatever RFC you want to read and it'll come up. So this is what an RFC looks like. All of them look exactly like this. So you see request for comments, RFC, and the number, RFC 1918. So yeah, you'll see it's basically a set of standards, but they have different categorizations. So you see this one is a best current practice. You have the authors here. You see Cisco is such a big company and they've had such a deep impact on the networking world. These guys write RFCs. So the RFCs are like the laws of the internet, so the laws of networking. And you see Cisco contributes it, RIPE, NCC, you'll see other people around, Juniper, and all these big companies, they all contribute to these things. And you can read through it. It is made to be fairly readable. It's not like, like a contract with a bunch of technical terms that made to confuse you. It is made to be very readable. So you can see here, the internet has grown beyond anyone's expectations. That is true. Like, you could appreciate that. So yeah, it is made to be very readable. So go ahead and read that if you want to. But I'll give you a summary in these few slides. So the RFC 1918 standards specify the following IP address blocks: 10.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. Whereas the public address space, these blocks here are the main components of the private address space, and the public address space consists of most of the remaining IPv4 addresses. We have some other multicast addresses and specially reserved addresses. You'll see a breakdown, a full breakdown of it here, because we just focusing on the private ones for now. But think of it as these are the main private blocks, and the public blocks are everything else. So you can see we have a ton of public address space, but it's still not enough, and you'll see why now. So let's focus on the private addresses a bit more. Private addresses were specially reserved to be used inside of networks. They are not routable or usable on the global internet, and should not be used between different organizations, which are ISPs or enterprises. However, they are also free for any organization to use, and can be used without prior approval by any authority, which is why they're so popular. Public addresses, on the other hand, are routable on the public internet, but require constant payments, justifications, and approval by registries. The main issue with these public addresses is that the global IPv4 address space has become exhausted. Right, so although they are 2 to the power 32, which is approximately 4.3 billion addresses, remember that every device on every network needs a unique address. Think about how many internet connected devices exist today, or think about how many internet devices you have. Smartphones, laptops, smartwatches, consoles, cars, servers, random Raspberry Pis, you have a bunch of sensors, cameras, everything is connected. So the regional internet registries, which is LACNIC for Trinidad and Tobago, they have all run out of public or global IPv4 address space. This has resulted in all network engineers having to use these private addresses to configure most of the hosts in their network, and using only public addresses for equipment that needs it. Only using public addresses for equipment that needs it. For example, your office PC likely does not need a public IPv4 address, but your web servers in the data center network likely need to be publicly accessible. The use of private addresses has led to other problems for us engineers, such as private addresses not being routable on the internet without a special feature called NAT, which we will discuss in a few classes down the road. And we also have issues with merging companies or networks. However, the problem is being addressed by the move to IPv6. So you can see more discussions here. But basically, the problem is we run out of IPv4 addresses, right? Nobody anticipated how big the network would grow. If you read up on the history of it, you'll see it was just a few isolated networks between some universities and some defense programs, and it was just made to be contained there. And then people started recognizing the importance of it, and people started getting excited about it. And in the last 20 or 30 years, the growth has been crazy. And you all know this, right? You all know how many things are connected to the internet, and how many more devices people keep pushing out. So everything is connected to the internet now. And that, of course, has had repercussions for addressing, because we need to have addresses for everything on the internet. And the problem is we ran out of addresses. So even though we had 4.3 billion addresses, it wasn't enough. For every device that needed to be uniquely identified, it wasn't enough. So right now where we are is that we basically have no spare public IPv4 addresses. The regional internet registries, these guys kinda try to make some available. So like some of the old giant blocks that they used to give out, some of that is not really being used. So these guys try to go back to those people and say, hey, if you're not using these addresses, you could give it back, and we could find other people who are using them. And some people go on the black market and they buy addresses kind of between themselves, and there are a bunch of other ways people are trying to get back addresses. But by and large, we out of addresses, and those things are just stopgap measures. So eventually we're going to need a bigger address space, which is where IPv6 comes in. But for the time, while we can't get public IPv4 addresses, we go to private addresses. So private addresses, let me see if I can think up a good simile here. It is sort of like owning land versus renting land, I guess. So owning land would be like your public addresses. You have to pay for it, and you need to justify it all the time, and you need to show the original internet registry why you need these addresses, and you need to be specifically authorized to use any public address, whereas private addresses is really anybody can use it, basically. I know rent, you need to pay either way, so it's not a good simile, but you get the point. So private addresses is freely accessible for anyone to use. You could go at home and you could address your PC with 192.168.1.1 without consulting anyone, and that is perfectly legal. And that is why everyone uses it. So for basic home addresses, for basic office PCs, printers, anything inside your network, people just use the private addresses anywhere there. Because it's so simple and easy to use, and they use the public addresses when they need to get stuff out on the internet, because you can't advertise your private addresses out to the internet, because then other people will be using those same addresses, and then people will get confused, right? Data wouldn't know where to go between two people who have the same 192.168.1.1 address, because everybody has that exact same address configured on their modem. So if we started advertising this out to the internet, data wouldn't know where to go. Whereas public addresses, because there's such a rigid addressing structure, and you have to pay for this and you have to sign a contract, there is only supposed to be one person with any particular public address. So with a public address, you could actually advertise like a web server, or anything, or any public facing server or piece of equipment or router or anything. So yeah, so that's basically the difference between private and public addresses, and now you can appreciate why we need private addresses. So due to the shortage of IPv4 addresses, we have been moving slowly to IPv6. So in an ideal world, we should have been on IPv6, 10, 15, 20 years ago. As soon as we saw that people were taking up internet services as quickly as they were, and as soon as we saw that people were running out of IPv4 space, we should have just cut it off and switched to IPv6 immediately. But we didn't. People just kind of stretched IPv4 as long as they could with a bunch of different features, I guess. So the main problem that IPv6 addresses, so it's a pun on, you see the pun. The main problem that it addresses over IPv4 is the address space size. So whereas there were 32 bits to create IPv4 addresses from, so remember our 32 bits that we subnetted from and everything, so every IPv4 address has 32 bits. IPv6 increases this to 128 bits. That is a lot more bits, leaving us with 2 to the power of 128 possible addresses. So 2 to the power 32 give us 4.3 billion. 2 to the power 128 is not just like, you can't just divide 128 by 32 and say is, I don't know, 3 or 4 times as much. 4? Yeah, it's not 4 times as much. It's 2 to the power of 128. So it's a lot of addresses, which is why I didn't put a number here. It's some kind of crazy number. So we can see we solved the problem immediately, right? We expanded our address space, and it opens up a whole new world of possibilities. So an IPv6 address is usually written like this. So this whole string here. Because we have so many bits, we need to write all of those bits in here. This number may look intimidating, but we will break it down and make sense of it. So don't worry, in the next few minutes, let's say in the next half an hour, you will know how to read this number and how to manipulate it and how to configure it on devices. Don't worry, it's just a slightly longer number than IPv4 address. So the first thing you should note is that each IPv6 digit is a hexadecimal number, as opposed to a regular decimal number in IPv4 that we are accustomed to. So the big advantage of IPv4 was that we use the same decimal numbers that we use in real life, right? So we use 0 to 9, and IPv4 numbers are 0 to 9. That's it. The big reason we've moved to hex in IPv6 is that we have so many more bits to represent now. So if we use decimal here in the same way that we use it for IPv4, we would do like 192.168.1.1.224.191.100.95. And it'll be a huge string. It'll be even bigger than this. It'll be all the way here, and we'll go over to the next line. And remember, the whole point is that you represent less bits with a decimal number than with a hexadecimal number. So hexadecimal numbers can allow us to represent more bits, and because of that, they go into more numbers. So hexadecimal numbers range from 0 to 9, just like normal decimal numbers, but then they can also go up A to F. So you can go 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then E. And E is a valid hexadecimal number, and all the way to F. So we actually seen hex numbers in MAC addresses. So those same digits that we had in MAC addresses, now we have them in IPv6 addresses as well. So hex numbers, were used because of the sheer volume of bits that we have to write in each IPv6 address. Each hex number represents 4 bits, giving us 8 groups of 16 bits to represent 128 bits for the address. So each hex digit represents 4 bits, and we have 4 hex digits per group, giving us 8 bits. So that may sound like craziness, but look at it here, right? So each one of these digits here represents 4 bits. So we have 4, and the next 4, and the next 4, then the next 4, and we have 4 of these numbers in each group. So basically between each colon here. So we have 4 bits, and next 4 bits, and next 4 bits, and next 4 bits. So that's 4 by 4. So that's the 4 by 4 here, and then we have 8 groups. So 1, 2, 3, 4, 5, 6, 7, 8. 8 groups. So 4 by 4 by 8 gives us the whole 128 bits that we need to represent. Yeah? So instead of writing, if you think this is hard, imagine writing 128 bits, 110000 all the way down. right? So better than doing that, we did this. So it's still long, but it's less long. Now the good thing is that these addresses can be shortened. Look at this address as an example. So we have 2803 CD80 00 DE 1456 0420 1500 ABCD 4430. So this is the full address. The shortened form of this address is 2803 CD80 DE. So CD DE there. We took out those two zeros, and then we wrote back the 1456 and then 420 instead of 0420, and then we wrote the rest of the numbers as they were. Notice how we have removed only the leading zeros but not any other numbers, including zeros in other positions. So you see we took out the 0 before the 420 but not after, so we didn't put 42. We put 0420 became 420, not 42. Same thing with DE, we removed the two leading zeros, and that's a rule in IPv6. So we can remove leading zeros but not trailing zeros. So we can't remove like the zeros here in 1500. If it was 0015, then no problem, remove these two zeros. But because it's after, you can't remove these trailing zeros in any group. So notice how we removed only the leading zeros but not any other numbers, including zeros in other positions. As another example, take 2803 00DE 000 0420 000 ABCD 4430. So we could again remove these leading zeros, and here you see we have 4 zeros, so we could remove these 3 leading zeros and leave this 1 0, and then 0420 we could remove that 0 again, and same thing with the 0. We could remove the 3 leading zeros and leave that 0 there. The reason we can't just remove this whole group here is that we need to ensure that we maintain the number, right? It's 128 bits, so it's easy for us to say we have 128 bits in total, and this is the number we have, so we could go back and expand it and just keep adding zeros here, because we know our one rule was that we can remove leading zeros. If we said we could remove leading zeros or trailing zeros, then how would we know how much to add in front or how much to add behind? So just an example again, if we could have removed leading zeros and trailing zeros, and we had DE here, we wouldn't have known if it was 00DE before, or if it was 0DE0, or if it was DE00. You see the problem there? But if we tell ourselves that the rule is only you can remove leading zeros, then if we see DE, we know those missing 2 digits have to be 2 zeros at the front. We know we couldn't remove anything else besides zeros, and we know we couldn't remove zeros anywhere else but at the start. So we could expand this address to get back this full address, and we need the full address to address the thing on the internet. Yeah? Okay, so I hope that makes sense. So again, we removed only the leading zeros. Since we know exactly how many bits each address contains, and we know that we are only allowed to remove zeros, we simply add back the zeros to get the full address. So again, just like I just described, because we know exactly what we were allowed to take out, we could add back those exact things and make back our full address, which in this case is only leading zeros. So you can't remove a 2, you can't remove a 8, can't remove a C or D, anything else. You could only remove zeros, and you could only remove zeros at the start. So when you add them back now, you have to remove zeros at the start. So now take 2803 CD80, and then this big 8 of zeros here, and then 0420, and the next 8 of zeros here. So the shortened form of this address is 2803 CD80, and then you see this double colon, so double colon there, 420 00 430, or 2803 CD80 00 420 double colon here 4430. Know that you are only allowed a single use of a double colon in an address. So we learned the first rule was that we could remove leading zeros. The second rule now is that if you have a long string of zeros like this, you could remove multiple groups of zeros. So instead of just removing the leading zeros here, you could just remove all of these zeros and replace them with a double colon. The rule is that you could only do this once. So you see these 2 groups of zeros here, you can't remove both of them and put 2 double colons. Again, the problem there is, if we put 2 double colons, we don't know how to arrange it in which place, right? If we have 1 double colon, we know, okay, we need 128 bits, therefore we add in a leading zero, we add in leading zeros, and then we check how many bits we need to add again, and we add as many zeros as we need here. If we had 2, then we could add in the leading zeros. We could add in leading, well, we wouldn't have these leading zeros starting. We would just have this leading zero here, and then we wouldn't know how many to add on this side and how many to add on this side. We would know if we had 4 zeros on this side, and then 2, 8, 12 zeros on this side, or 8 and 8, or 16 on one side. We wouldn't know how to allocate them. So that's why we only allowed to remove one set of zeros there. Yeah. So if we use the double colon in more than one place, we can't tell how many zeros we need to add back where. So consider this there. So we followed the rule. We only removed leading zeros here, and we only put one double colon there. We know that we need to pad out the leading zeros that we have removed from the shortened groups. So leading 0, and then all the leading zeros there, and then this is what we remained with, or double colon. Then we know that we have 128 bits, which is 8 groups of 16 bits in each address. So we keep adding groups of zeros to replace the double colon until we are at our required size. So you see here, we know we needed 8 groups of 16 bits. We had 1, 2, 3, 4, 5, 6 groups. So we know we missing 2 groups. So we add back 2 groups into this place where the double colon was, and we get back our full number. If we had 2 groups of these, we wouldn't know what to add back where, or how many zeros to add back where. Yeah, so now you know a bit about contracting and expanding IPv6 addresses, which is what this whole thing was about. So you can see how this address, this address especially, looks a lot simpler than this, right? It's a lot easier to write and it's a lot easier to read, which is why people like contracted IPv6 addresses. But machines, of course, don't understand this directly. They understand this full address, so they need to know how to expand this. Right, so that's contracting and expanding IPv6 addresses. So notice the /64 that we included in the addresses. So there, the 64 there, that we didn't really contract to expand. So we're going to talk about that now. So this /64 is not called a CIDR mask or a subnet mask or a subnet length as in IPv6. It is instead called a prefix length or a network prefix. Due to the much larger address space of IPv6, ISPs and regional internet registries deal with much larger prefix lengths. So of course we have 128 bits here, right? So these, before our subnet mask was like /24, /25, /26. Now we have like a /64 because we have 128 bits to deal with. So these prefix lengths are obviously going to be much larger. So LACNIC, which is the Regional Internet Registry for Trinidad and Tobago, usually assigns /32 prefixes down to organizations and ISPs. So before, they were assigning something like /24s and giving us 8 host bits to work with. Maybe if you're lucky, you would have get a /22. Now we get in /32, which doesn't sound that different from a /24 or something, but that's 32 bits out of 128, so we have way more host bits to play with there. This leaves 128 minus 32, 96 bits for subnetting and for host machines. So that's nice. The math doesn't work out as much, so you can't say there's 3 times as many addresses as the entire IPv4 space. That's 3 times the number of bits as the entire IPv4 address space. So if you put 2 to the power 96, that's how much addresses you're talking about here. And that's just one prefix. So that's, as in you as an organization, you could get a /32. And this is the entire IPv4 space. So nobody in the world could get the entire IPv4 space. This is 3 times as much as the entire IPv4 space. So you can appreciate just how large the IPv6 address space is. Compare this to /22 or /24 IPv4 address space that has been handed out to organizations in the past, which leaves only 8 to 10 bits for subnetting. So you can see how much more space we have here. Now, one major advantage of IPv6 is in the simpler addressing schemes. Rather than having variable length subnet masks, which was VLSM, according to the expected network size, and the need to conserve IPv space, the need to conserve IP space in the IPv4 space, sorry about that. Right, so as I was saying, rather than having variable length subnets according to expected network sizes and the need to conserve IP space, IPv6 primarily uses /64 prefix lengths for all LANs. So this is an RFC, this /64 recommendation. But basically what I'm saying here is, remember the whole thing about subnetting, the whole reason we did subnetting was try to maximize our IPv4 address space allocations, right? So we said we had a limited IPv4 address space and we wanted to maximize that to make sure that we weren't wasting IP address space. But because of how many addresses we have in IPv6, we're just going to use /64 for all of those LANs. So rather than leaving with a /31, you literally leave no address unused. A /31 gives you 2 usable IPs. Well, technically not, because I show if you did the calculations already. From when I said /31 the first time, you would have realized that it kind of breaks the rules, right? So it isn't an RFC. With a /31, you aren't supposed to have any usable IPs, but they made it specially for point-to-point links. So we could talk about /30s as more of a generic sense. In a /30, you have 2 usable IPs, and we use those 2 usable IPs, and that's it. We have no more space in that subnet. In an IPv6, in any IPv6 LAN, you have a /64, which means you have 64 bits for hosts, and that's 2 to the power 64. How many hosts can you address with 2 to the power 64 bits? That's crazy. But that is an RFC. That is the recommendation right now, which means that no matter if a network has 10, 100, or 10,000 hosts, the current best practice is to assign a /64 prefix to the router interface facing that LAN. Now recall that the entire IPv4 address space was just 32 bits long, while we are now assigning 64 bits for just one LAN, as in one tiny office network. So this may seem wasteful, but many of the features that are built into IPv6, which we'll discuss in a little bit, SLAC or EUI64, rely on prefix lengths of exactly 64 bits for end devices. So you shouldn't actually, you should never assign a prefix length smaller than a /64 for a LAN. The only exception allowed, of course, beside the specially reserved addresses like :1/128 for the loopback address, is with /127 addresses used for point-to-point links, which is at this RFC. So just like the /31 RFC I just mentioned, I can't remember the name, the number, the RFC offhand, but basically they had to make a special standard to just say, for this one special case, for point-to-point links, you can't use a /31 if you want. For everything else, you need to minus those 2 addresses for the network address and the broadcast address. And just like that, just because people wanted it in IPv6 as well, they made a special /127 for point-to-point links, just like the /31s, because they were so accustomed doing it. So this is what I'm talking about, right? This is what an IPv6 addressing scheme might look like for a small network. So you have 2 routers. Between those 2 routers, you have that special /127 block that you can use. And then for the LANs, for the networks that have hosts on them, you just assign a giant /64 address. So you see 001 /64, 002 /64. So whether it's 4 hosts or 1 host, however many it is, we could fit a bunch of different hosts in here. But the best practice is just to assign a /64 for however many hosts you need. Now, due to the large address space in IPv6, we don't need to focus on subnetting as much. Again, the whole reason we did subnetting was to maximize efficiency of the IPv4 address space, the whole address space. In IPv6, we just have so many addresses that we don't need to make everything so efficient. We simply need to learn to configure our IPv6 addresses on host machines and on equipment. On Cisco systems that support IPv6 addressing, some very old equipment may not support IPv6 addresses, but on the systems that do, we simply use the command IPv6 address and then the address /prefix mask, where A to H are the hex digits in our address and Pre is the prefix length. So just put IPv6 space address space and then 2803:1500 : whatever, and then /64. In fact, most of the Cisco commands for IPv6 can be found by simply replacing the word IP with the word IPv6. So I hope by this time you should have started some basic some basic IP configurations. I believe in the last lab you had that. So in the same way you'd have done like IP address something or show IP int brief, you just replace it with IP with IPv6. So for example, this is a screenshot showing the output of the show IPv6 int brief command, showing some IPv6 addresses configured on router interfaces. So yeah, here, good, you can see it. Show IPv6 int brief. Instead of show IP int brief, you do show IPv6 int brief. And you see some IPv6 addresses there. Yeah, just like that. It's fairly straightforward. Now there are a variety of ways that IPv6 addresses can be configured. One such way is through static configuration, which is in the same manner as IPv4. Another way is the use of stateless address auto-configuration, which is the SLAC word that I mentioned before. So SLAC stands for stateless address auto-configuration. So what SLAC does is basically a host machine uses the 64 bits of a prefix advertised to it, and it makes its own 64-bit end user identifier to add on, which is EUI end user identifier. And it uses those 64 bits of the prefix and its own 64-bit EUI to make that full 128-bit IPv6 address. So that's how SLAC works. Another way is through the DHCP v6 server, which works in a similar manner to IPv4 DHCP servers. So we'll discuss DHCP servers a bit more in IP services, which is a later class. Basically, DHCP is a way to hand out addresses automatically. So you know, like when you come into class and you connect to the Wi-Fi network, you don't know which IP address is assigned to your laptop or to your phone. You have a special thing called a DHCP server that handles that whole process for you. It basically says, hey, you want an IP address? Here, look one, that is free. And to the next guy that comes, it says, hey, you want an IP address? Okay, look, this guy took the last one, so you're going to get the next one in the available range. Yeah, so there are DHCP v6 servers which do very similar things. So lastly, some addresses can be automatically configured on interfaces. For example, link local addresses. So this is how we configure IPv6 addresses. You can do it statically. You can use this special thing called SLAC, which is a new thing in IPv6. Basically, what SLAC does is that the router advertises the prefix of the network. So in this case, like here, the router would advertise out this prefix and say, look, you network here, your prefix is this thing here, and that's your first 64 bits. To make your second 64-bit, the last 64 bits to get your full IPv6 address, which is 128 bits, you create your own EUI, your own end user identifier. And using that, it makes up its full 128 bits. And then of course you have the DHCP, which is the same thing as in IPv4, where the server just kind of hands you an address. And then of course you have some addresses that are just automatically configured, so like your link local addresses. So you'll have a lot of practice with IPv6 configuration, verification, and troubleshooting in the lab. So this is the topic that I mentioned, that is configuration. So in the lab you'll actually get hands-on with this and you'll see how to configure these addresses. Most Cisco equipment will need the IPv6 unicast routing command to enable IPv6 routing. You can read some more basic connectivity as here, but as I mentioned, in the lab you will be doing it. Right, so moving on, comparing IPv6 address types. So we didn't explicitly cover it in IPv4, but another method of categorizing network addresses is by the type of communications taking place, which corresponds to the different type of addresses present in IPv6 as well. So we have unicast addresses, which is one transmitter to one receiver. So it is like one person talking to one other person. That's unicast transmission. Multicast transmissions and multicast addresses facilitate one transmitter to many receivers. So multicast is used a lot in the video world, where you have one server transmitting a stream and a bunch of people tuned in to that one transmission stream. That's multicast. You also have anycast, which is one transmitter to the nearest receiver, So basically is like Google uses this a lot. So if we use Google services, we will be anycast to the address. We'll go to the nearest Google cache or the nearest Google server on our network. Whereas somebody in Japan might use the same Google address that we use, but they'll be anycast to a different server, which is just closer to them. So you will notice that broadcast addresses, which we talked about a lot in IPv4, those addresses are missing. So in IPv6, we have unicast, multicast, and anycast. We don't have broadcast. The concept of broadcasting has been removed from IPv6 and has been replaced by targeted multicast. So let's discuss this a bit more. Multicast addresses in IPv6 fall in the prefix FF00::8. So anything that starts with this is a multicast address in IPv6. To replicate the function of broadcasting in IPv6, special multicast addresses called well-known multicast addresses or solicited node multicast addresses have been reserved. So this is the targeted multicast that we just spoke about. So this is the concept in a nutshell, right? Remember, broadcast was just somebody standing up and shouting to everybody else in the room. That's broadcasting. In IPv6, we realized that this was very inefficient and it caused a lot of problems in our network. So what we did is we made up some special multicast addresses. So we basically said, if you want to listen to this guy shout, then tune into this channel, or then subscribe to this email thread, and you will hear everything this guy shouts about. But we're not going to let him shout to everybody. It's only if you subscribe to it, then you're going to get it. So that's what the solicited node multicast addresses or the well-known multicast addresses are about. So the well-known multicast address, think of it as a room that the guy is allowed to shout in. If you want to get it shouting, go in and tune into that. But if you don't want to, then you're very free to not, because there is no broadcast anymore. So one such well-known address is FF02::1, which is the all-node IPv6 address, meaning that messages sent to this address must be processed by all IPv6 enabled nodes on a network. So you see that this is one of the examples of a special well-known multicast address. So all IPv6 enabled nodes will tune into this to listen to special messages on this. So this might be like a government emergency channel, basically. So for example, RAs, which are routing advertisements, those messages will be sent to this all nodes address so that all nodes on the network can process and configure themselves with Slack as needed. So you have some more examples of multicast addresses and some more discussion on it here. But we'll go into this a bit more now. So another new type of address introduced in IPv6 is the anycast address. So anycasting was introduced in IPv4, but it was not as widely used as it could have been. Anycast addresses are not a special reserved range. They are simply unicast addresses that are configured on multiple devices. This breaks the rule of no duplicate addresses across networks, but it's used for particular special purposes. It lets devices speak to those devices nearest to them. Anycasting is particularly useful for providing services such as DNS and NTP. It allows for redundancy and optimization in the network. So I mentioned this for the Google servers before. So basically you have a bunch of servers around the world sharing the same unicast addresses, but it's configured on multiple devices. And the reason for this is that when any network device wants to go to these special addresses, they just go to the device nearest to them. So as opposed to going all the way around to Japan, people in Trinidad might go to a Google server right there in Miami, or even in Trinidad itself. But those nodes in Miami or in Trinidad would have the same addresses, the same anycast addresses as those servers in Japan or anywhere else in Asia. So it's particularly useful for services like DNS and NTP. So for example, yeah, you could kind of see it, it's a bit blurry. But you see this guy wants to reach this IPv6 address, and you see these servers all have that exact matching IPv6 address. But the difference is that the cost to server A and B and C are different. So this guy is obviously going to pick the guy with the lowest cost. Well, the router really will do that because that's the router's job. So the router will forward it to there because it has the lowest cost, which means it is the closest network terms, even though they all have the same address. Yeah. So the last type of IPv6 address is the one you're most familiar with, which is unicast addresses. Just like IPv4, unicast addresses facilitate one-to-one communication. So that's one person talking to one other person. Global IPv6 unicast addresses are taken from the range 2000:/3. So you see, this is just a very few bits we reserve here. This address space is going to be huge. We reserve 3 bits here, and then the other 125 bits could be, changed, and we could create a bunch of different networks from this. So these addresses facilitate global end-to-end communication across the internet without the need for NAT. So we'll discuss NAT in IP services as well in that next section. But the removal of NAT is a big benefit to IPv6 addresses because we use NAT a lot in IPv4. Because of the vast, well, you could click this link if you want to see, just some random IPv6 blocks and see how those address allocations look. But because of the vast number of global IPv6 addresses now available to organizations, most organizations are using these global addresses throughout their network. So the point I'm trying to make here is, instead of using the whole private address space versus public address space in IPv6, organizations are free to just go ahead and use these global addresses everywhere because they have so many. However, for special cases where organizations do not wish to use these global addresses, there are also unique local addresses available, which are kind of like private addresses. So these addresses begin with the prefix FD00::8, and they are similar to the private IPv4 addresses that we just covered. They can be used to route traffic within local networks, but cannot be routed onto the global internet. So just like private IPv4 addresses. So some more discussions on unique local addresses there. Now these unique local addresses are different from linked local addresses, which cannot be used to route traffic between networks, even inside of an organization's private network. So we said the unique local were like private IPv4 addresses, where you could you could talk to each other inside your own network, but not out on the internet. Whereas linked local addresses aren't like that. Linked local addresses, you can't even use that to route traffic between networks, ever. Not even inside your own private network. It's specific to a link. So linked local addresses begin with FE80::10 and are only used to route traffic within a single subnet. So within one link, or within one subnet, or within one network. All IPv6 addresses auto-configure linked local addresses on their interfaces, and they use these addresses to support protocols such as NDP, which is the Neighbor Discovery Protocol. So basically, these are like automatically configured addresses, which they use to set up other addressing and other protocols and other functionality. Now, just like IPv4 addresses, IPv6 addresses can be statically assigned or auto-configured. Static address configuration is almost the same process as with IPv4, except that we are now using IPv6 addresses. So we set up static addresses before. I think from the very first lab we did static addresses, which basically means you type in the address by yourself. Now, rather than configuring the entire 128-bit IPv6 address manually, you can choose to configure the device interface with the command IPv6 address, and then the prefix, and then the EUI64. So this is the EUI thing we mentioned before. This command statically configures the device with a /64 prefix and lets the device use the modified EUI64 method to configure the last 64 bits. So this is a sort of partial static configuration, partial auto configuration type of configuration. So basically what we're doing here is we telling the device, hey, I am assigning you these first 64 bits, and we type in that in the IPv6 prefix field here. So you type IPv6 space address space and the first 64 bits. Then we'll put a space and put the word EUI-64, and this would configure the device with the /64 prefix that we put in here, and it would let the device use the modified EUI64 method to configure its own last 64 bits rather than typing out the full 128-bit. So this method basically uses the device's 48-bit MAC address to calculate the last 64 bits by splitting the MAC address in half and adding the characters FE in the middle. But there is more involved steps. I believe, yeah, I have it here. So Cisco has a document on it here. So you see, this is the MAC address that we kind of saw before in when we touched layer 2 switching. So we split this in half, split, and then add FFFE in the middle, and then you invert the 7th bit from the left. Yeah, so you just check the bits here, and the 7th bit here, see it here. So 0 0, you take this, convert it to binary, and then you flip that 7th bit from the left, and you get your fully functional EUI64 address. So follow this link here, or this link, and get an idea of how the modified EUI calculation is performed. You will need to calculate it most likely, but just to get an idea of how to do it. Now, instead of configuring the prefix manually, you may also choose the IPv6 address autoconfig on the interface, which lets the device configure its address completely autonomously using the IPv6 arrays or routing advertisements from the router in the LAN. So we did it statically just now. Now we're going to use the autoconfig method. So this is what the autoconfig method looks like. So you have a router here. This guy just joins the host, the network, sorry. So he automatically configures his link local address. Remember, we said FE80 anything is link local. So FE80 and then this big address is his link local address. And he uses this link local address to communicate on his network. So you can see how this is so important now. He sends out a special message called a router solicitation or RS request to this special all routers multicast group. Remember we discussed the special multicast groups before, the targeted multicast groups. So this is another one of them. The RS message, he basically says, hey, I am on this network, please send me a routing advertisement so I could configure my own IPv6 address. When we discuss DHCP, you'll see IPv4 hosts kind of do something similar sometimes. So when the router gets this RS or router solicitation message, it replies with a router advertisement message, the RA message. Through this RA message, the new host will learn the network prefix. So this is like what a network prefix will look like. And then the new host will assign itself a new network prefix plus interface ID. So it will use that EUI64 method, and it will create its own full 128-bit IPv6 address using this prefix. Yeah. So that's it for today. Make sure you click the links here and go over all of these things. All of these. The way Cisco did these things is just to be able to contrast them. They didn't want you to be able to learn to configure all these things individually or calculate them or describe them in any depth. They just want you to be able to learn, compare the differences between them. So that's what I tried to cover there. I know it seemed like a lot, but this is what Cisco asked us to do here. So you should be able to understand just the basics of each of these things and be able to look at an address and based on the start of it, identify what type of address it is. So remember in all the slides I was kind of giving you a range. So let me see, right. So like this, link local addresses begin with FE80 :/10 and unique local is FD00/8. And the global is 2000 :/3. So try to memorize those because those are very easy ways of differentiating between this and this and this. And well, you know what an anycast address is. So it's not really linked. It doesn't have a range. It is just a special unicast range. Multicast has its own range. Let me see. Yeah, multicast addresses fall within FF00/8. So learn the FF00, and then now you know a bit about how to calculate the modified EUI address based on the MAC address and based on the prefix. So next class we'll go into verification of IP parameters and then wireless principles. And then in the class after that, we should be able to finish both of these. Yeah. Right, lab for this class. The lab is go back. Yeah. Right, so you should be on lab 6 now, which is subnetting, I believe. Yeah, so try and finish lab 6 and go over this material. As always, go through these topics, so that and this in the textbook, or if you could find it in the CBT Nuggets videos, and see what they have to say about it. So my method of teaching would have been very different to theirs. So it may have some things that I missed that they will cover, and they might be able to help you with anything that you may not be too clear on. And of course, come and ask me anything you want me to go into anymore, and I'll make some follow-up videos with it. Yeah, okay, thank you.